Okay. Okay, so I'm going to start with the presentation. So if people in the back could please sit down or go outside if they want to talk. Or thank you very much. Okay, so thanks for coming after lunch. I hope this talk will be somewhat exciting and won't put you to sleep after a nice lunch. But I'm going to talk about Flyclient today, which are super-like clients for cryptocurrencies. And I'll also try to answer the question why a blockchain is actually not maybe the best design. So this is joint work with Lulu Kiffer, and she's a joint first author, Loy Lu and Mari Zamani. And the problem that we're trying to tackle is that blockchains keep growing, and it's sort of now running a full node for any of the major cryptocurrencies is really a big requirement. And this is especially a problem if you think about mobile phones or really resource-limited clients, and how are they going to store 150 gigabytes, which is, I think, the size of the blockchain whenever I did this plot. The Bitcoin blockchain, then I did this plot. And Satoshi, even when writing the Bitcoin white paper, sort of foresaw this problem and said that, okay, maybe not everybody has to run a full node, but we can have something which is called a simple payment verifying client, or an SPV client, or also called light client, where the idea is that the light client only stores the headers of the blockchain and not the whole transaction data. And this allows you to reduce the storage by a lot, and it also allows you to do a couple things. You can verify that all of the block headers are correct, which means you can verify that the proof of work in this chain is correct, or that at least there's some certain amount of proof of work in a chain. And you can use this to determine which chain is the honest chain, using the longest or heaviest chain rule. So say you're presented with two different chains, all you need to do is check the block headers to know which chain is the honest chain and which chain is sort of adversarially created. And this all falls under the assumption that, in equilibrium, the chain with the most work will be the honestly created chain and will follow all of the rules of the network. So you can't verify all of the transactions because you don't have them, but you can verify specific transactions with some help. So if I receive some money, then a friendly full node can give me the transaction and give me a Merkle proof, so proof that this transaction was included in a certain block, and I just verify this proof and say that, can check that this transaction is valid and verify that I've received some money. And I cannot be cheated here. I can only be cheated in that someone could not tell me about a transaction, but no one can convince me that I've received money, which I haven't. So this has some very nice properties, that it doesn't grow with the number of transactions, and I can verify block inclusion, and it has some sort of applications which I won't go into today. But there's one problem that I want to focus on today, which is highlighted here in red, is that it still grows with the number of blocks in the blockchain. And especially if we think about blockchains which have a lot of blocks, then this means that you have actually a lot of data. So in Ethereum, which I'm going to use as the main example here, I'm sorry, but the SPV client is already 2.2 gigabytes. I think it might even be more. And this is especially bad if you have a multi-chain client which wants to have multiple chains or really quickly verify that a chain is valid. So how can we address this? So thankfully there was this sort of breakthrough work on so-called proofs of proof of work, or NIPO-POWs, which are non-interactive proof of work, where basically they showed that you can actually, by Kyriasis, Miller, and Zindros, and where you can show that actually this chain here has a sufficient amount of proof of work. So I prove to you, instead of giving you all of the block headers, and you can verify directly that it has a certain amount of work. The idea is that the prover can prove to you that it has a amount of work. And the nice thing is that you can do this with only a few hashes, only I guess some logarithmic or polylogarithmic number of block headers that you need to receive. And the core idea here is that for this NepoPower work is that basically if I create a hash chain with a certain difficulty, then I want to find a hash that x, such that hash of x starts with n zeros, then I will find 2 hashes en route which have n minus 1 zeros, and 4 hashes that have n minus 2 zeros, and so on and so forth. So what does this mean? It sort of means that the hash in the blockchain with the most zeros gives you a pretty good indication of how many blocks there are in the total chain. So if I know that a block, say the difficulty is constant here, and I know that a normal block starts with 50 zeros, then I can look at, I see a block with 60 zeros, and then I know that there's probably about 1,000 blocks in this chain. So the best quality proof of work indicates the quality of the host chain. And you can use some a really cool skipless design to do this. And so what is there's a few limitations with this. One of them is so-called bribery attacks or some sort of malicious attacks that what an adversary can do, it can sort of attack these high-quality blocks. And the problem here is that these high-quality blocks, they're really important now for these NepoPows, but they don't pay you extra mining fees, right? They don't pay you extra reward. They're just, So what an adversary can do is it can sort of try to keep these blocks out of the chain, and that won't, they deal with this issue, but basically that would make the proof very inefficient, and you don't actually have the benefit anymore. The bigger problem is that it cannot really, or the design has difficulty dealing with variable difficulty. So it is designed for a constant difficulty, which is not really realistic because we know that the difficulty changes a lot. So we have a new design for a new NepoPow, which we call Flyclient. And the core idea that we basically use is sort of this question, what is better than a list? So this sort of a standard, when you're in a computer science interview and you have a list and it doesn't really work anymore, it's not scalable, what do you use? So the answer is you use a tree, right? So instead of having a blockchain, what if we had sort of a block tree? And I don't mean a DAG design. What I literally mean is that we use a tree to connect all of the blocks. And so let's talk about trees in a second, or more specifically, so-called a special kind of Merkle tree, which is called a Merkle mountain range. So Merkle tree, the design is I take some leaves and hash them to build a tree. So every node is the hash of its children. And the Merkle mountain range is basically a Merkle tree, which has where it's easy to append blocks. And the other nice thing is that the nth tree also commits to the kth tree. So what do I mean by this? I mean that if I want to prove to you that, so if every block contains the Merkle root of if every block contains the Merkle root of the previous tree, what I can then do is I can prove to you that, here the third block, okay, so the third block, if I check, that the third block is included in this whole Merkle tree, I can also check that the third block contains the correct subtree here, right? The third block, this root here, which is committed to in B, should be the subtree of the large tree. And in general, right, I can very easily do these subtree proofs, where I prove to you that, okay, here I have some block here, and the block has a Merkle root, and I can prove to you very easily that this Merkle root is a subtree, or the right subtree, the subtree of the right size, of the overall tree, okay? And this property will be very important for our protocol. And these proofs are, like an inclusion proof. So checking this implies that all of these are in the whole tree, or that they all are agreed upon. So, so what is this different approach to super like clients? Well, as I said, instead of using a chain, a block chain, we use a Merkle tree. So every block now suddenly contains an MMR of all of the previous block, and we don't have this chain. We don't really need this chain structure anymore. So why is this helpful? Well, it means that I can refer to really old blocks, like a block that is, 1 million blocks ago, just with a very efficient Merkle path. So I can prove to you, say I only have the head, and I want to tell you, hey, this block, which was 1 million blocks ago, is part of the same chain. Well, in a classical blockchain, I would need all of the intermediary blocks to verify this. But with the Merkle tree, I just need log2 of 1 million, which is 20. So it's hashes, which is much more efficient. So to verify transactions now, I just need to store, our super light client just needs to store this one chain hat, which is very small. And then, I verify a transaction which is happened a long time ago, so I receive this Merkle proof that, this old header was part of the chain, and then I receive another Merkle proof that this transaction is part of that header. So now the big question is, how do we do sort of the Flyclient proof of work? Or how do we, or more fundamentally, say I am Alice and I have two people telling me this is the correct chain, and the other person that tells me this is the correct chain. How do I verify which one is the correct chain? So the assumption is that you can really reduce it to the case of you're just dealing with two people. It works with more people as well. But the assumption is that at least one of the guys that you're talking to is honest. Otherwise, you're sort of screwed anyway, so we don't really need to care about that. And then the malicious guy is significantly weaker than the honest chain. So the malicious guy only has a C fraction of the mining power, or more specifically, only a C fraction of the blocks that he mines are valid. So he starts mining, and he can only, he can create blocks, but most of them will have faulty proof of work. So this leads to sort of a very simple strawman, where the Alice just asks for a bunch of random blocks. So she asks, give me blocks 7, 3, 2, 10. And then the users have to give her these blocks, and they can do that very efficiently. Why? Well, because we have this tree structure where it's easy to refer to old blocks. And the idea is that the honest chain, will be a perfect proof of work chain. So all of the blocks will be valid. So, the honest guy can answer all of these queries. But the problem is the dishonest chain has a bunch of holes, right? Only a third of these blocks are valid. So with very, very high probability, if I keep sampling, I will find a block which is invalid. I will hit one of these holes with very high probability. So you could think if I have 1/3, then you need like 81 queries to have cryptographic soundness. So what is the problem with this strawman? Why is this only a strawman? Well, the problem is that the malicious chain doesn't have to start mining at Genesis, right? The malicious chain could fork really late only, do sort of a short fork, and then most of the queries would fall into the range created by the honest chain. So with all of even if I do 81 queries, I might not catch the adversary because it still has a third, basically a third of the blocks are holds, but only starting from this fork point, right? Before everything is valid, but starting from this fork point, a third of the or 2/3 of the blocks are sort of bad. But what it means is that if I knew this fork point, then we could apply the strawman idea again. Because what I would just do is I would sample in this small interval and apply the same protocol. So how can we know the fork point? Well, or let's just recap. Why can the adversary not cheat before the fork point, right? Why can't he take some valid blocks of the honest chain and insert them into into his fork? Or another question is like, why can't he take the honest fork and like just change one of the blocks? Well, basically the idea is that if I change one of the blocks here, right, then it would mean that all of the Merkle MMR proofs afterwards will fail. Okay. If this isn't clear, just trust me on this, but basically it's this property of this MMR, which we talked about before, which basically says I cannot cheat before the fork point. So the idea that we use in Flyclient, or one of the ideas, is that we can maybe not, it's maybe a little bit difficult to determine where exactly the fork point is, but it actually suffices to bound the fork point. So what we're going to do is we're going to sample enough blocks to say that, okay, if the adversary succeeded, then he must have forked somewhere late. He must have forked here, basically, okay? Because otherwise we would have caught him. If he cheated, either he's honest or not, then he cheated. But if he cheated, then he must have forked pretty late. So then I can just repeat this protocol and basically force him to fork later and later. And then the final step is just checking sort of L blocks to prevent short forks, which is a good idea anyway, because otherwise, the adversary can get lucky. So, so this is basically one of the core ideas of the protocol, right? I bound the fork point to be later and later. So then if we look at this, we can kind of draw this as a sampling distribution, basically saying like, what is the probability that I sample the block? And you can see that it sort of goes higher and higher the closer we get to the end of the chain. So 1.0 is the end of the chain. And the question is like, but this is sort of a step function. And a natural question to ask is like, why would this be a step function? Is this really the best thing that we can do? And basically, what we show in the paper is, using some like sort of fancy analysis, is that we can sort of get a smoother function, which is under some definition optimal for this. We use some differential analysis to find this function, which is sort of the optimal querying distribution for finding the adversary. And we can exactly like say, what is the probability that we catch the adversary with one sample, and then we can just repeat this k times to say, okay, get whatever probability we want. So the second thing is, we have to talk about variable difficulty Flyclient. So what if the difficulty isn't the same always? Well, so the idea is that basically I will commit to all of the weights, think of this as like the targets, now we are not looking for the longest chain, but we're looking for the heaviest chain. So what I'm going to do is I'm going to change my MMR such that it commits to all of the weights. It actually needs to have some more information, but for now, mostly it has the weights, and then every internal node is basically the sum of the weights of its leaves. So the root is, the hash root plus the total weight. So it's a Merkle sum tree. And then if I want to query a block, I use the same distribution, right, which we already normalized to be between 0 and 1. So if I sample from this distribution, I just get a number between 0 and 1. And say I get 0.4, so then I will just query the block which has 0.4, 40% of the total weight. So in the case of 70 here, this is 28, so I will need to query this block here, because 13 plus 13 is 26, plus 5 is, this is the block where the weight 28 is. The other thing is that, there's some subtleties here, where it's really important and that you change the difficulty transitions, because basically if this is important in blockchains in general, if an adversary can set the difficulty to be arbitrarily high, then he can just mine one block which is one super difficult block, and he can just get lucky and mine this block. So it's really important to verify that the difficulty transitions are correct, and see the paper for more details on this. So the protocol that I described was interactive, right? The verifier asked some questions, but this maybe isn't too realistic or isn't the sort of the nicest thing. What I really would like to have is that I can write down a proof, and this proof then can be transferred to other people. So if we look at the protocol, we can just see that the verifier just asks for random blocks, right? It's all he asks for. And what we can do is we can simply get the randomness from a hash function applied to the chain head, and so get this randomness not from a verifier, but get it from some public source. And this is also just known as the so-called Fiat-Shamir heuristic, which is a very classic tool in proofs. And it turns out that we can actually optimize the soundness a little bit, because basically creating a chain head is already difficult because I need to solve a proof of work for it. But, or creating a different chain head is difficult. But the nice thing is right now a prover can just create this one full node, one nice full node, can create this Flyclient proof, write it down, and send it to the whole world, and people can forward it, and everybody can verify it. So here are some evaluations where basically these different plots are different levels of adversaries. So basically how powerful the protocol has a parameter, which is basically how powerful do you assume the adversary is? What fraction of the blocks can he actually produce? And the dotted function is the work difficulty. And we can see, that even, the proofs are between, I think this is, they're between like a kilobyte, maybe, or up to a kilobyte, and maybe for the most aggressive setting, like 3 kilobytes versus 2.2 gigabytes, right? The proofs are also a little bit shorter than Nepopau's. So how can we deploy this? Well, the easiest thing, as always, is to do a hard fork or start a new chain, and just instead of using a blockchain, use the smarter design, which is a block tree, which also has other benefits. But and this is actually what some currencies like Grin, who's here, Beam, Mimblewimble, which is here, Grin and Chia are doing already. And the other thing is you could soft fork, so you could force that the MMR is in the Coinbase. Or the third idea is something really nice, which came out of the original Nepopau paper, which is the so-called velvet fork, which basically says you don't need to fork at all. You just need some nice person who periodically commits to the MMR in a transaction. And basically, you can, if every third block contains this MMR, then the proof size will increase by a factor of 3. So ideally, it would be in every block, but it's okay if it's not in every block. So sort of the more miners agree to do this, or the more blocks have this transaction, the more efficient the protocol. So that's a really nice property because it sort of is an uncontroversial fork. Here are some references, and yeah, so thank you very much.